All right. I think what I'm gonna do is I'll start with question 4, just to make sure that I'll be able to cover up to question 4 with the time that we have. I think for the first 3 questions, some of them are repetitive, so so we'll start with we'll go backwards. In other words, we'll start with question 4, and then yeah, we'll see if we'll be able to finish all of the questions in question 1, but otherwise we'll just pick whatever is relevant for that with a given time. So with question 4, it's combining everything we've learned so far about forces and acceleration. A spider is descending vertically along a strand of silk, as shown in the picture to the right. So we'll consider the silk as something that's not very elastic. So we'll treat it like a rope or a string. A string would probably be a better description than a rope. Instead of an elastic band, for example. So what forces are acting on the spider? Okay, we know that anything that has mass will have weight. So the spider should have a weight force acting on it. Just turn on my pen. So it should have a weight force acting on it, and yeah, what other force is acting on the spider? It's the one that's holding it up, the tension on the strand of silk. Okay. Is there any other force? We will assume here, it's not given in the problem, but we'll assume that air resistance is negligible and friction is negligible. So there are essentially just 2 forces acting on the spider. It's weight and the tension on the string. Now, next, sketch a free body diagram of the weight and tension forces. Remember, in free body diagrams, if we can, we should sketch the magnitudes to yeah, the magnitudes. And it says it's, I think the problem, I think I have the old version of the problem. The one I have printed in the solutions manual, in the one from Stream, I think, says that it's descending with constant velocity. I think I don't know if this is the updated question, but yeah, the spider is descending at constant velocity, meaning acceleration is 0 if your velocity is not changing. So according to Newton's first law of motion, the magnitudes of the forces should be equal but opposite in direction, so that the net force is equal to 0. So if you draw your free body diagram, the lengths of the tension and weight forces should more or less be equal. So weight force is always directed downwards, and tension is along the string and pointing away from the object, which is the spider, and that's why it's vertically upwards. Right. Next question, a gust of wind blows the spider to the right, and the spider remains attached to the strand of silk. But now it's the silk is at an angle to the vertical, and we're not given the angle. It's at an angle to the vertical, but we're not given the angle. What we are given are the components of the tension force. So the components of the tension force are given here. Sketch the components to show the magnitude and direction of the net force. So the net tension force. So look at the x component, it's negative. So a negative x component means that that x component should be directed to the left, right? So that should be a Tx is equal to negative 2.5 newtons, right? And then your y component is upwards. So your y component is positive. Oh, that's too big. y component is positive, so that means it's upwards. Now, be careful when you're drawing your y component. You might be tempted to draw your y component this way. You have to draw your y component so that the head of the x component meets with the tail of the y component. So this is your y component, which is 7.5 millinewtons. Sorry, I now missed the prefix there. There's actually a prefix of millinewtons. So millinewtons, the prefix milli, which you learned in the last two lectures, milli means times 10 to the minus 3, right? The prefix milli means times 10 to the minus 3. So you need to include that. Yeah, don't forget to include that milli. So also the y component should be times 10 to the minus 3 newtons to account for the milli newtons there. So it means Ty is 0.0075 newtons and Tx is negative 0.0025 newtons. Yeah, right. So these are the x and y components, and to show the magnitude and direction of the net tension force. So your net force now will go from the tail of the first to the head of the last. So this will be your net tension force, the diagonal side of the right angle triangle. Right, and your angle will be measured with respect to the positive x-axis. Right. Next question, work out the magnitude. So if you have any questions, just feel free to pop it in the chat box as we go along, or just unmute yourself and ask directly. So work out the magnitude of the tension force. So we see here the magnitude is the diagonal of a right angled triangle. So the magnitude of that will be from Pythagoras theorem. Right, which says that the if you have a right angled triangle, it doesn't matter how your angle or your triangle is oriented, as long as you have a 90 degrees there. Let's name the hypotenuse as C and the horizontal as A and the vertical as B. Pythagoras theorem says that the hypotenuse C, the diagonal, is equal to the square root of horizontal squared plus vertical squared. So your diagonal here is the tension. The A here, the horizontal, is the x component of tension, and the vertical is the y component of tension. So therefore, the tension force should be equal to the square root of x component. It doesn't matter whether you put the negative or not, because you're squaring anyway. The negative will disappear. Yeah. So get the square of the x component, square of the y component, add them all up, get the square root, and you should get 7.9 times 10 to the minus 3 newtons, or 0.0079 newtons. Work out the angle the tension force makes with the vertical. It actually specified that you are calculating the angle with respect to the vertical. So let's redraw our So this is the y component of tension, the x component of tension, and then you have the tension force here, right? And it says angle, the angle that it makes with the vertical. So that means it's this angle that they want you to calculate. Right, the basic trigonometric relationship tangent theta is equal to the side opposite the angle divided by the side adjacent to the angle. Okay, the side opposite the angle is the x component, and the side opposite, the side opposite the angle is x component, and the side adjacent to the angle is the y component, tangent theta. Right. And then you now do just theta to get rid of the tangent. You do the inverse of the tangent. That will be inverse of the x component divided by the y component. Right. So we know the x and y components. We just substitute it there. The x component is 0.0025. And the y component is 0.0075. So you should have an angle of 18 degrees. Yeah. All right. Any question about this? Okay, let's go to question number 3. We are given the free body diagrams with forces along the x and forces along the y. First question, find the net force along the x-axis, that's net F net x, and the net force along the y-axis, that's F net y. So when you're getting the net forces, you separate x and y axis. So for the first case, okay, F net x, you have 230 newtons, but it's to the left. So you have negative 230 newtons. The negative there is because it's pointing to the left. So that will be a negative. And then 170 newtons is pointing to the right, so that will be a positive 170 newtons. And that will give you a net force of 80, negative. Negative 60 newtons for the x component. The y component, you have 200 newtons upwards and 200 newtons downwards. So that should be a net force of 0. So I'll just write down the working 200 newtons upwards, and this 200 newtons will be negative. It's pointing downwards, so that will be a net force of 0. For the second scenario, there is one vector that is diagonal. So that means you have to get the x and y components of this diagonal vector. So you have to get the x components of this 100 Newton vector and the y components of this 100 Newton vector before you can add up all the vectors along the x and the y. So let's do that. So the x component here is the side that's adjacent to the angle. So that will be 100 cosine 36.9 degrees. And the y component will be 100 sine 36.9 degrees. And you can do that in the calculator. What's that? Cosine 36.9 times 100, that's 79.97 newtons. And for the sine, 36.9 sine 36.9, times 100 is 60.04 newtons. Okay. So now you have, you can do now the net force along the X. Okay. Net force along the X, you have this 40 newtons that's directed to the left. Okay, so that will be actually a negative 40 newtons. You have the net force, the X component of this 100 Newton force that's directed to the right. So that's 79.97 newtons. So that's 79.97 newtons minus 40. And those are the only two forces along the horizontal or along the X. So this will be 39 point something. That's approximately, that's about 40 newtons. Right? And then for the vertical component F net Y, right, you have this 100 Newton force that's upwards. So you have the 100 Newton force that's upwards. And then you have, again, another 100 Newton force that is coming from the Y component of this 100 Newton force. So this Y component that is also directed upwards. So you have a plus 60.04 newtons that's coming from the Y component of this 100 Newton diagonal force. And then you have this negative 160 newtons because it's pointing downwards. So you have negative or minus 160 newtons, and that will all add up around 120. Yeah, wait, I think. Let me do the sine and cosine once again. I think I'm in. So sine of 36.9 will give me 60. Yep, 60. Yeah, right. So you have there a 0 Newton force for the Y component, roughly 0 newtons. Yeah, almost 0. You're right, Oksana. Okay, and then for the last one, you only have two forces along the Y, they're opposite. So you have this plus, so you only have an F net Y. You have 140 newtons minus 50 newtons. Yeah, you have a negative 50 that's going downwards right there. So that will be 90 newtons. That's positive. Right. The second question asks for the acceleration using net force. So Newton's second law of motion, net force equals mass times acceleration. We already rearranged this in class. The acceleration will be net force divided by the mass. So if you want to get the acceleration along the X, acceleration along the X and the acceleration along the Y. So let's do it for the first case. So A, the acceleration will be equal to acceleration along the X will be equal to the net force, which is minus 60 newtons divided by the mass is 20 kilograms. So you have minus 30 meters per second squared. So you can just, minus 3 meters per second squared. So you can just right away put meters per second squared as your unit because your force is in Newton and your mass is in kgs. Yeah, kgs. Right, for the acceleration along the Y, that's 0 because your net force along the Y is 0. Right, for the second question B, so the acceleration along the X will be the net force along the X, which is 40 newtons divided by the mass of the object, 16 kilograms. That should give you an acceleration of 2.5 meters per second squared. And for the Y component, the net force is 0, so your acceleration would also be 0. Okay, and then for the last one, you only have an acceleration along the y. Net force along the y is 90 divided by the mass is 5 kgs. So that will give you an acceleration of 18 meters per second squared. Okay. Right. Okay, so let's move on to question number 2. Here we want to find the net force. We're given the components, x and y components, and we want to find the diagonal which corresponds, which is equal to the net force. Right, so a common mistake I see here is to connect these two vectors to get the net force. Okay, this is wrong because yeah, you're connecting the head to the tail of the net force. You have to draw your parallelogram first before you can get your net force. You have to copy your F1x up here. Should do a dashed line. So let me do a dashed line here. So that's your F1x, and you should also copy your F1y. Yeah, keeping the directions the same, right? Because you're just copying. So the directions of the arrows should be the same as well. And the net force will actually go from, the net force will go from, let me change colors here. The net force will go from here where the tails of the two vectors to the heads of the two vectors. So notice how when you're drawing the net forces, all the tails are together and all the heads are together as well. Right, so here, yeah, for the magnitude of the net force, let's do A, that's Pythagoras theorem. So the net force F1 is equal to this, Pythagoras theorem. You get the x component, square that, get the y component, square that, and get the square root. And then you should have 7.2 newtons for F1 net. Right. For the second vector, you do again the same thing. Right. You do the parallelogram method, copying all your vectors, and your net force should go this way. F2 net. So notice how, yeah, how you'll find points where the tails, all the tails meet and all the heads meet, and that's the reference point for drawing the net force. So calculating the magnitude of the net force for B, for F2 net, again, you do Pythagoras theorem, 3 squared plus 7 squared. Yeah, technically this would be a negative 7 squared, but it wouldn't matter because you're doing a square, that the negative will disappear. So you should have 7.6 newtons. Yeah. And I think, yeah, we're running out of time, so I probably won't do the calculation in detail for everything. Let me just draw here for part C, question C. Right, you have your vertical component, keeping the same directions for your forces, and then drawing your net force from where all the tails meet to where all the heads meet. You can again, once again, you can get again the magnitude using Pythagoras theorem. Right, so I'll just set up the equation, 5 squared plus 5 squared, and you can do the calculation. Well, yeah. It's easy, 7.1 newtons, I think. For the last one, yeah, so this is where the parallelogram method is now very useful. So you copy your forces, right? And the net force is where all the tails meet, going to where all the heads meet. And we don't have to calculate the magnitude for this because it's not, you have to get the x and y components and then do the whole add up all the x and y components before you do Pythagoras theorem. Right, for the angles, for the direction, okay, angles for part A, angle is equal to arctangent of the y divided by the x component. Okay, so for part A, that's tangent theta, arctangent theta of 7 divided by 6. That's 67 degrees. Okay, your F1 is in the first quadrant. So notice how F1 is in the first quadrant. So you keep the angle as it is. For the second case, you do the same calculation. So that will be arctangent of the y component, which is, where are we? So second case, 7 divided by 3. Oh, I think I did the wrong. This should be. Yeah, arctangent of 7 divided by 3 for question B. That should give you 67 degrees. But notice how the net force is in the fourth quadrant. So the final direction should be 360 degrees minus 67 degrees. That's 293 degrees for the final. Or you can also say final is equal to minus 67 degrees. So that's the only time when you can do a minus is when your vector is in the fourth quadrant. And then for the last one, you do again tangent theta, arctangent theta equals opposite over adjacent. Well, they're both 5, the y component and x components, they're both 5. So that's 5 divided by 5. You'll get an angle of 45 degrees. But notice how the net force is in the second quadrant. It's going up to the left. So your net force here is in the second quadrant, F net. Okay, and we've seen that if your vector is in the second quadrant, your final angle should be 180 degrees minus whatever you've calculated, 45 degrees. So that's 135 degrees for the final angle. All right. 4 divided by 6. Yeah, you're yeah, so for the first one, so question 1, so the y component is 7, right? Y component is 7 and the x component is 6. And that's why it's 7 divided by 6. It's not 4 divided by 6. Let me just check. Yeah. Oh, right. Yeah, you're right, Oksana. Yeah, it's a confusing. That's 4. This is actually the F1Y. Yeah, so you're right. So for question number 1, it's actually 4 divided by 6. 4 divided by 6, and that should give us 49 degrees. Yeah. 4 divided by 6 and then getting the arctangent of that, 34 degrees. Yeah, thanks Thanks for that correction. It's yeah, it was a bit confusing in the drawing there. Yeah, I think I'll just do the first one is the same as the example we did in class, so let's skip that. And then for the second one, yeah, I don't know, we should just, it's 11. Maybe the trickiest one will be the last one. So maybe I'll just go over the last one. Do you think? Yep. Any feedback as to which ones we want to go over for question 1? We probably have time for maybe 1 or 2. Okay, I'll do the last one. Maybe I'll do the last one and then we'll see how that goes. But it's 11. If you have somewhere to go, that's fine too. So for the last one, for our equation to work, for our x, f5x, you know, that's the cosine theta. And then for the f5y, that's the f sine theta. For our sine and cosine equations to work, for x component to be a cosine function, we should measure the angles relative to the x axis. So here we need to get, say, this is the x component f5x, and this is the y component f5y. So that means we need to know the angle relative to the x-axis. So we need to know this angle here, right? And that angle there will be 90 degrees minus 20. We are given the angle between the vertical component and the diagonal vector, right? But we know this is 90 degrees. So to get the angle theta, that's 90 minus 20 degrees. So you can do now the usual. So for question E, f5x will be the diagonal, which is 10 newtons times cosine 70. Your angle now will be 70 degrees instead of 20 degrees. Giving you an x component of about 3.4 newtons. And for the y component, you have 10 sine 70 degrees, 9.3 newtons. Yes, angle will be 70 degrees. That's right, 1e. Yeah, I think we're working backwards now. For D, you have your x component and your y component. So your x component f4x and your y component f4y. Okay, so you also do the same thing. So f4x will be 12 cosine 60 degrees. Okay. Because the angle 60 degrees is given relative to the x-axis. So you can just go right ahead and use it as your angle theta. Yeah, and maybe I'll let you do, yes, 13 newtons. Yeah, maybe I'll just let you, I'll just set up the equations and then you'll do the calculations, plugging that into the calculator. And for the f4y, that will be 12 sine 60 degrees. Right? So, and it's actually the same for everything. Or maybe I'll just write the answer so you can check if your calculator is set in the right setting. So 12 cosine 60 degrees is 6 newtons. 12 sine 60 degrees is 10 newtons. Right. For C, you can also again draw your x component. F3x, and your y component F3y. Okay. The angle is again measured relative to the x-axis. As long as the angle is measured relative to the x-axis, you can go right ahead and use the cosine function to get the x component. So F3x will be 15 cosine the angle is 30 degrees. And that will give you 13 newtons. And for the y component, you have 15 sine 30 degrees. Oh, no. Yeah. So notice how it's just either the sine or the cosine that's changing if you're getting the components. That will give you 7.5 newtons. Right. And for B, question B, it's the same thing. You can have the x component F2x and the y component F2y. Again, the angle is measured relative to the x-axis, so you can go right ahead and get the x component using the cosine function. So F2x is equal to, should have 20 and 37 degrees. So that's 20 newtons cosine 37 degrees. That will give you about 16 newtons. And then for the y component, it's 20 sine 37 degrees. And that should give you 6.8 newtons. Right? Yeah, so you can actually see a pattern here when you're getting the x and y components, right? The force is the same and the angle is the same. So you have, you're just changing whether it's a cosine or a sine. And if the angle is measured with respect to the horizontal, the x component will always be a cosine and the y component will always be a sine. So for the x component, it's 10 cosine 70, y component, it's 10 sine 70. It's the same force, 10 newtons, it's the same angle, 70 degrees. It's just changing whether it's cosine for x-axis and sine for y-axis. And yeah, for question A, it's very similar to the one we did in class. F1x, the angle is measured relative to the x-axis, so that's a cosine 30 degrees. So F1x will give you 8.6 newtons, and F1y will just be the sine instead of the cosine. So the F or the y component will be 5 newtons, 5.0 if you want to include two significant figures. Okay. Okay. So calculation for the angle of 2C. This one. Okay. Calculation for the angle of 2C. So for the angle of 2C, you are actually getting this angle here. Yeah. So when you're getting angles, look for the right angle triangle. So that will be this triangle here that you're considering, because that triangle contains your x and y components. So you're getting this angle theta. You're getting this angle theta here. And angle theta is arctangent. It's this equation here. Arctangent of the y component divided by the x component. So your y component is this one, which is 5 newtons. And your x component is this one, 5 newtons. And that's why the angle is arctangent of 5 divided by 5, which is 45 degrees. Okay. your final angle should be measured with respect to the positive x-axis. So your final angle should be, your final angle should be this one, measured with respect to the positive x-axis. And that's why we had to add, we had to subtract 180 degrees, because your force is in the second quadrant. This is from this side to that side, that's 180 degrees. But what you want is this angle. This is your final angle, right? What you've calculated is this one. What you've calculated is this 45 degrees. Okay, and that's why your final angle should be 180 degrees minus 45 degrees. Yeah. The negatives, so are they negatives left and down for 1C? Right. So 1C, yes. So yeah, if you include the direction, then they should be negative for 1C. But when you're calculating the using cosine and sine, yeah, when you're calculating using cosine and sine, you will get a positive number. So finally, yeah, you're right. You should, if we put the direction, we should put with direction. With direction, that should be a negative, which is downwards. Yeah, they're both negative. There should be negative 13 newtons and negative 7.5 newtons. But I think the question just asks you to find the magnitude or the size. So we didn't care about the directions in this case. But yeah, if you were asked to give the directions as well, then you should check whether it's pointing to the left or pointing to the right. Yeah, so you're right about that. Okay. Yeah, we did do everything, but we're 13 minutes over time. Yeah, so thanks for sticking with me. Are there any other questions before we end related to this workshop or anything else? Yeah. Right. Otherwise, thanks everyone. I'll see you on Friday. Right. Have a good day and see you then.